All right, greetings and salutations, physical science class. Today we're going to be looking at acceleration graphs. So we're kind of moving from the formula to the graphs, depicting the acceleration of an object in a visual format. But we still need to use our formula, so we'll get into a little bit of that as we move along here. So let's get into it. Our objective today is that you'll be able to read and describe how slope is related to acceleration on one of these velocity versus time graphs that I'm talking about. So if you've taken, let's see, geometry, yes, I believe geometry and algebra, we've talked about slope. So you should know a little bit about slope, x divided by y. So let's look at this a little bit. So you should have your document out for this lesson. You should have it open, and you should be able to see it as well as see this recording so that you can fill in the blanks as we move along. So on your worksheet it says, on a graph of velocity versus time, what is the independent variable? Well, the independent variable on a velocity versus time graph is time itself. So that means that the dependent variable must be the other one, and that would be a good assumption, a good prediction to make. So the dependent variable is, in fact, velocity. Notice in parentheses there with time on the independent variable, it has an S in parentheses. Well, that stands for seconds, just in case you didn't know, but I'm sure you probably did. And then, of course, on velocity, in parentheses, it says m/s, so that would be meters per second. Meters per second. Just want to make sure you knew what those units were, why they were there. So whenever we measure time, we measure it in seconds. That's our base unit, so to speak. And in velocity, our base unit would be meters per second. All right, so the slope of a velocity versus time graph tells you the object's acceleration. So when we plot it on the graph, you'll see that we create a line, and that line is what's called a slope, and that gives us a visual representation of the object's acceleration. So remember, when we calculate the slope, we're going to take the rise, or what we'd call the change in y, the y-axis, over run, or divided by run, which is the change in the x-axis. So the x-axis is always the horizontal, and the y-axis is the y. So if it goes up to and over 4, your slope is going to be a line drawn from where the x and the y cross up to that point 2 up and 4 across. You're going to draw a straight line between those 2 points, and that's going to be your slope. So let's take a look at this in action. So here, this graph shows a car's velocity, which is y, over the time that it takes that car to travel. So each of these vertical lines, or the lines that go up and down, would be a 1-second increment. And you would read that across. So this is actually the x-axis, even though we're marking the lines that go up and down, we're marking them as we go across. So each one moves left to right, just like we read. Okay, so that's called the run. This would be the x over here. Let's see if I can get a nice color here. So let's go with green for x. This is the x-axis. Of course, it's right here too. It's already typed in for us. And so we would have 0 here, 1, 2, 3, 4, 5, and so on, all the way out to 6, 7, 8, 9, 10, 11, and the last one is 12. Okay? So that's our x-axis, and this is seconds. It's marked in seconds. So that's our run. So green was run. Let's go with purple for our y-axis, our rise, the y-axis. And it's going to be measured vertically, up and down. So this is 0, 1, 2, 3. You get the idea. 4, 5, 6, 7, 8. So 8 is the highest point. Okay? That's not a very good 8. I know. All right. So we've got our axes marked out with our number columns. So let's go. Rise over run. What we would do would be to count up. So our rise from 0 is 1, 2. We got to go all the way up to here, this point here. Okay, so this is going to be 1, 2, 3, 4, 5. So our rise is 5. And our run is 1, let's go back to green, 1, 2, 3, 4, 5, 6, 7, 8. So our run is 8. Now notice that I didn't go all the way up here. Because we're looking for where these two lines intersect, right? Where our y and our x intersect along our slope. Oh, we could have done this one here, but I asked for this one up here. This one would be 1 over 2, right? That could be 1 over 2. It goes up 1 and over 2. But we were looking for this point over here. So our acceleration is going to be 5 divided by 8, which gives us, don't have a calculator on me. Let's see, 5 divided by 8 would be about, let's see, half would be 4, it'd be about 0.67. So we'll go with like 0.67, 0.68, somewhere in there. So our acceleration is this, meters per second. So every second, the car is 0.67 meters per second faster than it was the previous second, is what that tells us. Okay? So every second, our car is traveling 0.67 meters per second faster than it was the previous second. That's what acceleration is, the change in speed or velocity. All right, let's try looking at some more velocity versus time graphs. This one shows us a lot more information than the previous one did. And it asks us, what does the graph look like when the acceleration is 0? Well, there should be a flat horizontal line. So what are some flat horizontal lines on our graph here? Well, we have the line segment from B to C. That would be one point at which the acceleration is 0. So it's maintaining the same speed. Now that doesn't mean the object has stopped. It simply means that the object is no longer increasing its speed. Likewise, segment D to E is also a point at which there is 0 acceleration, even though there's still speed or velocity. And then F to G is another horizontal line segment, telling us again that there's 0 acceleration. Okay? Now what type of line, would it be positive or negative, corresponds with increasing speed? Well, it would have to be a positive line, meaning it needs to be pointed up and not down. And it would need to be going up, as I just said. So we'll use purple for that. A to B is a line trajectory pointing up. It's going up, right? So that's going to be a positive acceleration. C to D also is going up. That's a positive acceleration. And G to H is positive acceleration. Now notice I skipped E to F. Well, E to F is actually going down as you move as you move across the time continuum, that one is actually traveling down. So that means there's a deceleration going on, meaning that the object is slowing down. So now we actually talk about that specifically. So what type of line, is it positive or negative, corresponds with decreasing speeds? Well, it has to be a negative line, as I mentioned, and it has to be facing down. So again, E to F is our line segment that goes down as you move through time. And so that one is our decreasing or decelerating line segment. So basically from the period of 8 seconds to 10 seconds, that object is slowing down. So what does a steep line mean compared to a shallow line? So that would be, this would be steep, this would be more shallow, almost horizontal, it would be less steep, right? This would be steeper. So what does that mean? Well, it means that it has higher acceleration. So that means that the object's velocity is increasing quickly over time. Or conversely, it can have it'd still be higher acceleration, but the object's velocity would be decreasing quickly over time. So the steeper the line, the more severe, or the more quickly the object is either speeding up or slowing down. Okay, here's another graph. It's similar to the last one that we saw, and it wants you to take a moment to try to label the 4 places listed below. So the first one is 2 places where the person's speed is not changing, and then the second part, B, is find the place where the person is slowing down, and then C is find the place where the person is speeding up with a high acceleration, and the place where the person is speeding up with a lower acceleration. Alright, so pause the video and draw this out on a sheet of paper. If you have graph paper, it makes it a lot easier, but if not, just use plain paper. Notice the little graduation marks on here. You see them? So that would be each second, right? It'd be 1, 2, 3, 4, and so on. And then you have them over here too, 0, 1, 2, 3. Okay? Alright, so let's clear that. Alright, back to my pen. Alright. So hopefully you paused the video and you plotted these out. Let's see if what you plotted out matches up with what I do. So the 2 places where the person's speed is not changing would be here, or you could select the whole line segment, and here. So that's A. I'll just do different colors for each one. The place where the person is slowing down would be this line segment here. That's B. Place where the person is speeding up with high acceleration, that's key here. So let's go with red for high acceleration, would be here, comparatively speaking. And then where the person's speeding up with lower speed, we'll do that in a light blue. Lower acceleration would be here, because the line is less steep. See, the red one is pretty steep, and the blue one is more shallow, not as steep. Okay? So if you got all those, then you're good to go. You're really starting to understand this stuff. Here I'm going to have you draw your own simple velocity and time graph for the following scenarios. Now, on your worksheet, you have these grids, so you can just use them as is. You can just number them. So remember, 0 is down here, and 0 is down here. 1, 2, etc. You get the idea. 1, 2. All right. And so it gives you a little scenario, and you need to map out the the acceleration of this car. So the car stopped at red light for 3 seconds. The light turns green and it speeds up for 4 seconds and then continues driving at a constant velocity. So go ahead and give that a try on your own. That's going to be part of the exit ticket. There are 3 of these, so you're going to do all 3 of them for your exit ticket. Actually, I'm going to do this first one, and then you'll do the last 2 as your exit ticket. Do this one as well, but I want to do this one for you just to make sure, because it's laid out a little differently. So I want to make sure that you understand this. So let's finish our number scheme here. 3, 4, 5, 6, 7, and 8. And 3, 4, 5, 6, 7, 8. Alright, so it's 8 and 8. 8 across, 8 up. So this is our y-axis, and this is our x-axis. Remember, y over x is the formula. Alright, so the car stopped at a red light for 3 seconds. So I'm going to use purple. So it stopped at a light for 3 seconds. So 1 second, 2 seconds, 3 seconds. The light turns green and it speeds up for 4 seconds. So I'm going to go 1, 2, 3, 4. And then it goes into a constant velocity. Okay? So it stays the same speed. So it's at 0 meters per second here, and then it accelerates for 4 seconds, and then it goes flat. So that should be what your graph looks like, and that's how you do that. Okay? So stopped for 3 seconds, accelerates for 4, and then continues driving at a constant velocity. Now the next one you're going to do on your own. I'm not going to do this one for you. This one says a student is walking slowly towards her bus stop at a constant velocity. Then she starts running because she sees the bus is about to pull away, and then she slows down to a walk again because she missed the bus. She couldn't catch it. So you're going to draw that out on this graph, and then the last one is going to be scenario C. It says a track runner begins the race by speeding up very quickly, then reaches his maximum speed, which he maintains for the rest of the race. When the race finishes, he stops immediately. So that's going to be a tricky one. Think about how you can represent stopping, going from, and that stopping is actually a deceleration. So you're going to have a line that goes down, and it says immediately. So how steep is that line going to be if he's stopping immediately? Okay. Now don't think about what it would be like in the real world. Just go by what it says here. We're suspending reality for the moment. Okay? So work on those and come to class, and we shall work on some other examples of these different types of time versus velocity graphs, or velocity versus time graphs. All right? Thank you. Bye.